an S of t that's continuous, like a sine wave or something else that's a periodic, and it has to be periodic. If it's continuous, the Fourier series, the technical word is converges for each t. In other words, this side and this side are equal for every value of t as long as S is continuous. The issue comes when it's discontinuous. And if S of t has discontinuities like the square wave or the periodic pulses we looked at, the Fourier series does not converge at the points of discontinuity. It turns out that for a square wave, I plot a square wave here for a second, and you can evaluate the complex exponentials all at t over 2 and add them up. And it turns out it's going to give you a value, even though for the square wave I didn't assign a value. And the value it's going to assign, it turns out, is the average of the values on either side of the discontinuity. So it's going to assign a value of 0 to what happens at precisely t over 2, even though I didn't define it, of course. So it doesn't converge. It gives a value, but it may not be the value that you want. So how do we think about this? Well, I do want to point out something. So if you look at the difference between the signal you have and this finite Fourier series approximation, you look at the power in that error and you take the limit as k goes to infinity. It turns out you can prove that you always get 0. So this is the error in the approximation, k-term approximation, and it turns out that error, as the number of terms gets big, has no power, has no energy. There's no difference between the two in terms of power. So the mathematician said it does really work, except you have to change your definition of equality to mean this. Okay, two things are equal if the difference between the two has no power, and this is called convergence in mean square or mean square equality, and it really is the power in the error that becomes the important thing. So for all intents and purposes, the Fourier series really does work. It's just that it doesn't quite work at points of discontinuity, but we don't care about points of discontinuity anyway. What do I care? But it is equal. So the Fourier series really does work as far as we're concerned. All right, so let's look at the properties of the Fourier coefficients. So again, here's my time domain, if you will, representation of the signal as a function of t. Here's my frequency domain representation as a function of k, which governs the Fourier coefficients. And here's how you get between the two. And let's look at the properties. So first of all, if S of t is real valued, you can show that the harmonics that are negatives of each other are complex conjugates of each other. Well, we've seen this before. This says that the real part of c minus k is equal to the real part of ck, and that the imaginary part of c of minus k is equal to the negative of the imaginary part of ck. And so this was conjugate symmetry that we talked about before. The real part is even, the imaginary part is odd, and so you can show that the Fourier coefficients obey this, and I think if you check all the previous examples we've worked on, they've had this property. Furthermore, if S of t itself is real and even, it's an even signal about the origin, then the c sub minus k is equal to c sub k, which means the c sub k's are always real, and they're also even. That's what even means. So you have real and even for the signal. The Fourier coefficients are also real and even. And if you have an odd signal that's real valued and odd, and that's what odd means, it turns out the Fourier coefficients are also odd, but they're pure imaginary. Okay, that's what it takes to be consistent with this result up here. Okay, so very important symmetries that you can use to simplify your life. And essentially what I'm doing is figuring out what the negative frequency axis is from the positive frequency axis. Okay. So I can fill in what happens at negative harmonic numbers, negative frequency, from what's happening at the positive indices. And one little cute property here that's very important. Suppose I delay the signal, what is its Fourier coefficient going to be? So the idea is that I have, let's say, a square wave. Okay, and it turns out to make it periodic, we've got to do that. And now I delay it, let's say by a little bit, so it does this. You would think that the Fourier coefficients would be related somehow, and it turns out they are through this linear phase right here. The phase turns out to be dependent on the delay, and then the frequency of the Fourier coefficient enters in. But it looks like a linear delay. I mean, a linear phase. Delay in the time signal corresponds to multiplying the spectral version of the signal by a linear phase. It's linear because this argument up here, which is 2 pi, I'm going to write it a different way, tau times k, is a linear function of k. Okay, well, through the Fourier series, we can study a signal in both time and frequency. They're equivalent to each other. We can go back and forth, and this is going to be a very convenient thing for us to use to explore how signals, what their structures are, and how systems operate on them. So, for periodic signals, the Fourier series is the way we obtain the signal spectrum. The signals can exist in either time or frequency domains. This is really an important thing. You may start, we have started with signals as being defined as functions of time, and we use the integral here to figure out what its spectrum is. I'm going to give you an example in the next video where we start with the superposition, and that's the natural thing to do. In other words, start with a frequency domain specification of the signal and see how it's built, what the resulting signal is. So either one is perfectly valid, and this is very exciting and will help us figure out how signals and systems work in modern information systems.